Hello and welcome to this lecture. We are now going to start looking at various operations we learned with matrices, right? So, once we had matrices, we started doing algebra with them. Before that, we did this transpose, we did inverse, we did sum, we did product, we did powers. So, what happens to the eigenvalues when you do all that? Okay, so we'll at this point, whatever we can say, we'll say. Later on, we'll keep adding to this as we go along. Okay, so let's start by looking at the matrix and its transpose. Okay, so an important topic. How are the eigenvalues of A and eigenvalues of A transpose related? How are the eigenvectors related is the question. Okay. So, let us begin with eigenvalues. So, we know eigenvalues of A are solutions of this determinant equation, right, the characteristic equation which is determinant of A minus lambda is 0. What about A transpose? It is A transpose minus lambda is 0. On the face of it, you may think that these two are not related, but actually they are very closely related. In fact, if you look at A minus lambda I the whole transpose, by the properties, we know it is A transpose minus lambda, lambda is a scalar, I transpose, but what is I? I is just a diagonal matrix with 1, so transpose is equal to itself, so it is A transpose minus lambda I, okay. This is okay, I hope you see this is a very interesting little observation. So, because A minus lambda I whole transpose is the same as A transpose lambda I, and determinant of A and determinant of A transpose are the same. If you do a transpose, determinant does not change. So, determinant A minus lambda I, which is equal to determinant of A minus lambda I the whole transpose, is actually determinant of A transpose minus lambda I. So, these two equations for A and A transpose are exactly the same. They came from the different matrices A and A transpose, but once you do the minus lambda I and take determinant, you will get the exact same equation. These two are the exact same equations. If they are the exact same equation, their solutions are identical. So, the eigenvalues and their algebraic multiplicities are identical for A and A transpose. Okay. So, A and A transpose have the same eigenvalues with the same multiplicities. What about eigenvectors? Let us look at eigenvector with eigenvalue lambda naught. Okay. So, if you are doing that, for A, what happens? Geometric multiplicity of lambda naught, this eigenvalue, is the nullity of A minus lambda naught I, which is nothing but n minus rank of A minus lambda naught I. This is okay, this we knew before. What is it for A transpose? Again, you will get a similar equation, right? For A transpose, geometric multiplicity of lambda naught is nullity of A transpose minus lambda naught I. This is true. And that is nothing but this A transpose minus lambda naught I is the same as A minus lambda naught I the whole transpose, and then you get n minus rank of A minus lambda naught I the whole transpose. Now, what is the rank of a transpose? It is the same as the rank of the original matrix. So, you get n minus rank of A minus lambda naught I. So, not only are the algebraic multiplicities identical for A and A transpose, the geometric multiplicities of eigenvalues are identical for A and A transpose. Okay. But the eigenvectors will be different for A and A transpose. Okay. So, in fact, here is an interesting little terminology. The eigenvectors of A are usually also called right eigenvectors of A. The eigenvectors of A transpose are often called the left eigenvectors of A. Okay. They are the sort of right eigenvectors of A transpose are called the left eigenvectors of A. Why is that? You can see this little equation, right. So, it is very easy to write down. So, supposing you have a right eigenvector for A transpose V is equal to some lambda into V. If you take transpose on both sides, what happens? V transpose A becomes lambda into V transpose. So, notice V transpose, it is like a left eigenvector, right. If you multiply by V transpose on the left, it is invariant. V transpose A becomes lambda V transpose. Okay. So, the right eigenvector of A transpose becomes the left eigenvector of A. Okay. So, this is a common terminology you will see quite often. People will give a matrix, find the eigenvalues, right eigenvector, left eigenvector. For every eigenvalue, there is a right eigenvector and a left eigenvector. Okay. So, it has got to do with this relationship between A and A transpose. Okay. So, this terminology we will not use too much in this class, but anyway, it is good to know that because quite often you will see packages will talk about left eigenvectors, right eigenvectors. Right eigenvectors for A are the usual eigenvectors. Left eigenvectors are basically the eigenvectors of A transpose, which is basically multiplying by a vector on the left and getting invariance. Okay. So, this is transpose. So, let me show you an example just to show you how this works. We will go through this very quickly. We will look at this 1, 1, 3 example, and if you look at transpose, it is 0, 1, 1 here, right. So, algebraic multiplicities are the same, nothing changes. If you look at lambda equals 1 eigenvalue, you've got A minus I like this and A transpose minus I like that. Okay, so it's sort of, it transposes. Once it transposes, geometric multiplicity remains the same, even for A minus 3i, it's the transpose, but then the actual eigenvectors start changing. For A minus I, you have this minus 2 and all. For A transpose minus I, it is just 1, 0, 0, 0, 1, 0. Okay, and for A minus 3i, you've got 0, 0, 1. Here you've got half, half, 1. Okay, so I hope you see why this is true. The eigenvectors exactly will change just because of the transpose nature, but the arithmetic, algebraic multiplicity and geometric multiplicity and the eigenvalues themselves remain exactly the same for A and A transpose. Okay, so let's move towards inverse. Okay, so inverse is another very important operation. What happens to eigenvectors when you invert? Okay, so first thing is we will have have a linear transformation T. We've been not talking about linear transformations too much, but hopefully you see that T is represented by A. Now we'll say A is an invertible matrix. So this T is an invertible operator. So this A becomes an invertible matrix. So T inverse is also an operator from Rn to Rn, and the matrix A inverse is n by n invertible matrix corresponding to this guy. Okay, of course determinant of A eigenvalues are all non-zero, right? We know that that's true. You can't have a zero eigenvalue, right? So we saw the relationship between zero eigenvalue and rank of the matrix. Rank here is n, so no zero eigenvalue. So let's start with an eigenvector with eigenvalue lambda naught. So here is a very, very easy and simple relationship. Notice here, so if you have an eigenvector for A with eigenvalue lambda naught, AV equals lambda naught V, right? So we know that that's true. AV equals lambda naught V. Now you can divide by lambda naught because lambda naught is not 0, right? So you divide by lambda naught and then multiply by A inverse on the left, right? So A has an inverse. So you get here 1 by lambda naught into V has to be equal to A inverse into V. Okay, notice this equation. These two are exactly the same. So AV equals lambda naught V if and only if A inverse V equals 1 by lambda naught V. Okay, so you notice what do you see from here? It's very, very simple relationship, right? So this vector V under T is invariant, right? Under T, V goes to lambda V. So clearly under T inverse, which simply maps lambda V to V, it will still remain invariant, right? V itself is invariant. V goes to lambda V. If it's invertible, lambda V will come back to V. But V remains invariant in both cases. So from here we see that the eigenvectors are identical for A and A inverse, okay. In fact, you can say more about eigenvalues also. See, notice here, if V became an eigenvalue, corresponds to an eigenvalue lambda naught, at A inverse, V will correspond to an eigenvalue of 1 by lambda naught, right? That's what this equation means. So the eigenvalues are going to have like a reciprocal relationship, and it's quite immediate here, but you can write down an equation and then show it entirely in an easy way. If you look at eigenvalues, you go back to this determinant equation, A minus lambda is 0. For A inverse, it's A inverse minus lambda is 0, but then what happens here, right? So A inverse minus lambda, if I multiply by A, I get I minus lambda A, and then if you pull minus lambda out, you get A minus 1 by lambda I. Okay, so if you take determinant on both sides, you see determinant of A, which is non-negative, times determinant of A inverse minus lambda I is equal to some lambda times determinant of A minus 1 by lambda I. So determinant of A inverse minus lambda I is 0 if and only if determinant of A minus 1 by lambda I is 0. Okay, so this is an important relationship. So from here we can quite easily see that if lambda naught is an eigenvalue of A with algebraic multiplicity k, okay, because this determinant of A minus lambda naught I is actually determinant of A minus 1 by lambda naught I equals 0. From this equation you can conclude, right, from here you have 1 by this lambda naught inverse 1 by lambda naught is an eigenvalue of A inverse, and the arithmetic multiplicity also remains exactly the same. Okay, not arithmetic, I'm sorry, algebraic multiplicity. I keep saying arithmetic all the time, sorry for that. The algebraic multiplicity of lambda naught inverse is also the same as the algebraic multiplicity of lambda naught. Lambda naught for A had an algebraic multiplicity k. Lambda naught inverse for A inverse will have the same algebraic multiplicity k. That's what it means. Okay, it's not like it's not okay to say, I think, arithmetic. I mean, algebraic multiplicities, eigenvalues are different, but the algebraic multiplicities remain the same. Geometric multiplicity also remains the same, right? Because eigenvectors are identical. So geometric multiplicity of lambda naught and geometric multiplicity of lambda naught inverse are also the same. Okay, so I have not quite said it here, but hopefully that's also easy to see. So when you have invertible matrices A and A inverse, the eigenvalues go reciprocal. A lambda as the eigenvalue here will become 1 by lambda here, but arithmetic multiplicities and geometric multiplicity, I keep saying arithmetic multiplicity all the time, it's algebraic multiplicities and geometric multiplicity remains exactly the same for lambda naught and 1 by lambda naught. So this is about inverse. So we've seen transpose, we've seen inverse. Let's move on to sum product. Okay, for sum product you can actually say precious little, you can't say too much, you can only say under the condition of a common eigenvector. So this is an important thing to remember. Supposing you have two matrices A, B which are n cross n, supposing they have a common eigenvector, this is very important. Supposing A and B share a common eigenvector, what does that mean? There is a vector which is invariant under both A and B. Under both A and B it doesn't vary. Okay. So if V is an eigenvector of A with eigenvalue lambda A and an eigenvector of B with eigenvalue lambda B, eigenvalue can be different, but it has to be an eigenvector. So what happens? AV equals lambda AV, BV equals lambda BV. Okay, so this is true. So once under this condition, we can say a little bit more about what happens to V when you look at the sum. If you look at the sum A plus B, V is an eigenvector of A plus B with eigenvalue lambda A plus lambda B. And if you look at why that, this is very easy to see, this is how it is. And if you look at the product AB, V is an eigenvector of AB with eigenvalue lambda A lambda B. Okay, this is also very easy to see. In fact, I've said sum and product here. You can compose them in so many ways. You can do, for instance, A plus A square B. Okay, and then if you hit it with V, V will become an eigenvector of that with lambda A plus lambda A square lambda B, right? So all of those, any algebraic relationship I have with A and B, if I have a common eigenvector, that's very important. Common eigenvector is very important. Once you have a common eigenvector, any algebraic combination of A, B, B, A, B, whatever, this V will remain invariant. And the corresponding algebraic combination will give you the eigenvalue. Okay, the V itself will be the eigenvector. Okay, I hope you see this. I've showed it only for sum and product, but whatever operation you do, as long as it's like some A, B, A square, B, A cube, whatever, only the algebraic addition and multiplication are there, you will get the a common eigenvector of A and B will end up being a eigenvector for that algebraic combination also. Okay, so I hope you see that. Okay, so we've dealt with transpose, we've dealt with inverse, we've dealt with sum and product as well. Okay, so finally we'll go to powers. Okay, so this is power of a matrix. You have a matrix A and then you have A power k, which is A multiplied with itself k times, right? So this is a repeated application of an operator. Okay, so let's say you have an eigenvector of A with eigenvalue lambda. Now what will happen? If you look at A square V, okay, it is A times AV, but AV is lambda V, right? And that lambda will come out, so you will have one more AV, and that is again another lambda V, so you get lambda square V. Okay, so I hope you see this. It's very easy to show, and you can keep extending. A cubed V will end up being lambda cubed into V. This is quite easy to show why this is true, and you can extend this. A power k into V becomes lambda power k into V. Okay, so this leads us to this very important relationship. If you have V as an eigenvector of A with eigenvalue lambda, then V is an eigenvector of A power k with eigenvalue lambda power k. Okay. So in fact you can reverse it also. It's a little bit complicated. If you have an eigenvalue for A power k, you can also say that something should be an eigenvalue of A, but I'm not going to say it here. It's a little bit confusing. So but this relationship from A to A power k is very clear. So if A has an eigenvalue, eigenvector with an eigenvalue, the same becomes an eigenvector of A power k, except that this lambda power k becomes the eigenvalue corresponding to that. Okay. Okay, so finally we'll do this curious looking algebraic operation, which will end up being very important when we study something called diagonalizability of a matrix. Okay, so let's see that. This is a eigenvalue type relationship. Here you need two matrices. A can be any matrix n cross n. This S has to be invertible, okay, because I'm going to do SA S inverse. When I'm doing S inverse, S better be invertible. Okay, so if you have an invertible, I'm doing SA S inverse. This has a name. This is called a similarity transform. Okay, so it's a pretty big name, but it's called a similarity transform. We'll see a little bit later about this in the ensuing weeks of the course. Okay, so let's look at the eigenvalues of A and compare it with the eigenvalues of SA S inverse. Okay. So eigenvalues of A will come from by solving determinant A minus lambda is 0, SAS inverse will come from solving determinant SAS inverse minus lambda is 0. But notice what happens here. If you look at SAS inverse minus lambda I, it is exactly the same as S times A minus lambda I times S inverse. How did I get this? If you multiply this through, you will see you will get SAS inverse minus lambda I, because SS inverse will become I. right. So, this is a very, very interesting relationship, and because of this, determinant of SA S inverse minus lambda is 0 if and only if determinant of A minus lambda is 0, because determinant of S is non-zero, determinant of S inverse is non-zero. You take determinant on both sides, you get determinant of the LHS as determinant of S times determinant of S inverse, which will in fact cancel and give you 1, and it will become equal to determinant of A minus lambda. Okay, so that's the important relationship here. In fact, these two are equal. So determinant of SA S inverse minus lambda I becomes equal to determinant of A minus lambda I. So those two are identical. So because those two are identical, the eigenvalues and their algebraic multiplicities are identical for A and SA S inverse. Okay, so this is quite easy to see. Okay, so that's why this SAS inverse seems interesting. When you do SAS inverse, even though you're changing A dramatically, you know, if you take some arbitrary matrix, do SAS inverse, it looks like A is changing dramatically, but its eigenvalues remain the same. So you will see a slightly more abstract reason for why this is true later on. It's sort of obvious at some level, but we'll see that interpretation later. Okay, what about eigenvectors? Okay, so let's start with an eigenvector V with eigenvalue lambda naught for A. Okay, and we look curiously at this SAS inverse multiplied on the right with S times V, not V, but S times V. This SV is chosen appropriately. You will see why, because if you do SV, this S inverse S will now cancel, right? So this S inverse S will cancel, you will simply get S times AV. But what is AV? V is a eigenvector with eigenvalue lambda naught for A, so AV will become lambda naught V. So lambda naught will come out and you will get SV. Okay, so now this is an eigenvalue eigenvector equation for the matrix SA S inverse, right? SA S inverse multiplied by some vector is lambda naught multiplied by the same vector. So this SV is an invariant vector for SA S inverse if V is invariant for A. Okay. So from there we conclude that if you have an eigenvector V with eigenvalue lambda naught for A, SAS inverse will have an eigenvector SV with eigenvalue lambda naught. Okay, so this actually means that every eigenvector you do, you multiply by S, you will get an eigenvector for SAS inverse. So in fact, the geometric multiplicities are also the same. So SAS inverse as in and A have the same eigenvalues, same algebraic multiplicities, same geometric multiplicities, except the eigenvectors are changed by just multiplication by S. That's all. S times V, you will get a thing. And S is an invertible matrix, right? So if V1, V2 are linearly independent, SV1, SV2 are also linearly independent. So they can't change that. It's like invertible operation, right? So you will get the same properties. All of them will be true. Okay. So this sort of concludes our look at algebra and eigenvalues. Okay, so this is quite important. Quite often, while you have a matrix and you know its eigenvalues, maybe multiple matrices and eigenvalues, these matrices will combine. They'll start multiplying. We saw that in the dynamic systems example and all, right? They'll start multiplying, combining, and all that. And you have to argue about the algebraic the eigenvalue properties for the algebraic combination. So there, knowing the individual eigenvalues, if they have common eigenvectors, etc., you can say a little bit more about the eigenvalues of the algebraic combination. Okay, so with this, we'll stop this lecture. Thank you very much.